Hello, champions. Today we are going to begin our unit on forces, and the first thing that I want to do is to define in AP Physics how we consider forces. Now, at a very rudimentary Bill Nye the Science Guy kind of level, you all might know forces as a push or a pull. And that's a very simplistic way of approaching it. But I want you guys in AP Physics to be more familiar with forces. And by definition, a force is an interaction between two objects. So a force is an interaction between two objects. So if you have only one object, then you cannot have any forces acting on that object because forces are interactions between two objects. Contact forces. So these are probably more familiar to you. This is anything that touches the object in question. All right, some examples of contact forces would be, in the way I generally denote forces is with a capital F and then a subscript giving an indication of what type of force it is. The most general would be an applied force. Right? This is anytime there is a push, somebody is pushing on something, you could simply call that an applied force. We have something called a normal force, F subscript N, and the normal force is also known as a surface support force. And so this is a surface support force. There is also forces due to friction, F subscript FR. There is force due to tension. That would be a rope pulling. That, again, the push or pull, push being an applied force, pull being a tension force. There are all kinds of forces. There are buoyant forces. There's force due to air resistance. Just a whole host of contact forces. In contrast to the bevy of contact forces, we have field or range forces. This is where the interaction between the two objects does not involve contact. And the most familiar one of these, and the only one really that we will be concerned with in AP Physics 1, is F subscript G, gravitational force. The other two field forces that you may or may not be familiar with are magnetic and electrostatic. So when we are dealing with forces, what we do is we draw a free body diagram of our system in order to be able to identify all of the forces that are acting on that system. The free body diagram, this consists of a dot. A dot represents whatever object or whatever system we are looking at the forces on. So in this first example here, we're asked for a free body diagram for a bucket hanging from a rope. Now, the first thing that we will do is we will draw the system. We'll sketch the situation, and then identify the system and circle it. All right. So in this case, the system is the bucket. Right. So the reason why we circle the system is because we can identify all of our contact forces by whatever breaks our system circle. So in this case, there is the rope that breaks our system circle. So when we draw a free body diagram, again, we draw a dot that represents the system, bucket, and then there is a tension, a force of tension that is on the bucket by the rope. And that's the only contact force that breaks our circle, our system circle. Now, there is a field force, the gravitational force, also acting on our system. And so there is a gravitational force on the bucket. Right? Well, if a force is an interaction between two objects, what is the object that causes this gravitational field force? Because gravity is not an object. Gravity is the description of the force. The object itself that is causing that is Earth. Right? So there is a tension on the bucket by the rope, and there's a gravitational force on the bucket by Earth. And in this case, the problem states that this bucket is simply hanging. Right? So because this bucket is simply hanging, we know it's not moving. We say that the upward force and the downward force, the upward force by the rope and the downward force by the Earth are equal, and we put marks on the force arrows identifying that fact. Right. The second example here is free body diagram for a book sitting on a table. So we've got a table and we have a physics book sitting on the table. Again, the first thing that we want to do is identify the system, a book, that is our system, and then circle the system. We circle the system so we can identify what breaks the circle. Again, in this case, the dot represents the book. The only thing that breaks our circle is the surface of the table. Right? So there is an upward force on the book That, again, is our surface support force. We call that, again, a normal force. And when we get more into this, I'll explain in more detail why it is called a normal force. But that is our upward force. It is the only thing that is breaking our circles. This is the normal force on the book by the table. And then again, there is the gravitational field force, force of gravity on the book by Earth. And again, this book is not doing anything, so these two forces must be even, must be equal. The way, what we say when these two forces are equal, or when we are talking about a combination of forces, is we talk about the net force. The net force is essentially the vector total of the forces. Sometimes you will see this written as F subscript net. It is also sometimes written as the Greek letter. This is a capital sigma. So sometimes it is written as sigma F. That is the sum of all the forces. By convention, we say that forces upward are positive, forces downward are negative, forces to the left we tend to call negative, and forces to the right we tend to call positive. In this case, well, in both of these cases, the net force acting on the bucket and the net force acting on the book is zero. And the unit that we use when we are talking about forces are newtons. Newtons are the unit of force, obviously named after Sir Isaac Newton. All right, acceleration. Acceleration is always in the direction of the net force. And in this case, or in these cases, with the net force being equal to zero, in both of those cases, then the acceleration is 0 meters per second per second. Right? In this case, the bucket is hanging; it's not moving. Therefore, obviously, the acceleration is 0. This book is sitting on a table. Again, not moving. Obviously, its acceleration is 0. Let's look at a different example here, where if I've got a pail of water, right? I pull up the pail with 96 newtons of force, and the weight of the bucket that pulls down against me is 40 newtons. once again, the first thing that we need to do is to identify the system. In this case, it tells us that the system is the bucket. So this is the system. The next thing that we do is we circle the system. And we circle the system so we can identify what breaks that circle around the system. So the free body diagram of this is going to be the bucket or the pail, and the force that is affecting this bucket upward is an applied force on the bucket by me, and the field force downward is the gravitational force on the bucket by Earth. And then this case, we actually can quantify. So we know that this upward force is 96 newtons, and this downward force is 40 newtons. So what is the total force? So F net, which is equal to sigma F, the sum of all forces, is equal to 96 newtons upward less 40 newtons downward. So the net force acting on this bucket is 56 newtons upward. And because there is a net force on this bucket upward, the direction of the acceleration is also upward. Right, in these next two examples, we are looking at drawing free body diagrams of a book falling to the floor and of a child pushing a box across the floor. So in this first case, we've got a shelf from which a book has fallen. This book is falling off the shelf. So specify the system. And so the system is a book. So the system is the book. Motion diagram. Well, as you saw from your free fall lab, the motion diagram for this is dots that start close together and progressively get further and further apart. That is the motion diagram. Free body diagram. For a free body diagram, we begin with a dot that represents the system. So this is the book. Having identified the system, I circle the system. And the reason I circle the system is so that I can identify what contact forces are acting on this book. In this case, the book is just falling through air, and in this class we disregard air resistance, so there is no contact force on this book. The only force acting on this book is the gravitational force downward. So the only force acting on this book is Fg on the book by Earth. Now you'll notice that in each of the free body diagrams that I've drawn, I've made sure to identify the system, one object, and the agent acting on that system, in this case, the Earth. Because as you recall, a force is an interaction between two objects. So in this case, the two objects are identified in this force nomenclature on the book by Earth. So that's the free body diagram. Label all forces with their agents. Okay, this is the agent, Earth. Indicate the direction of the acceleration and the direction of the net force. So the acceleration is down and the net force is down. And that takes care of all of the specified requirements of this question. And the final one on this page is a child pushing a box across the floor, and it moves at a constant velocity. So we've got this box on the floor, and it's a pretty big box, but we've got this child pushing this box. All right, so this child has freakishly long arms. But this child is pushing this box across the floor. It moves at a constant velocity, right? A constant velocity. So what does that tell you? Well, if it's constant velocity, what is the acceleration? Right. The acceleration for constant velocity is 0 meters per second per second. It's constant. So we have our diagram. Now we need to identify the system, right? A box, that is the system. So we circle the system. We circle the system so we can identify what breaks the system circle. And in this case, the system circle is broken by two things, the floor and the child pushing on the box. So our free body diagram, again, begins with a dot indicating our system, the box. The child is pushing on the box to the right, so there is applied force on the box by the child. As we had with our previous examples, there's a gravitational force on the box by Earth. And just like we'd seen in the book on the table, the floor here exerts a normal force upward. So Earth exerts a gravitational force downward on this box. The floor exerts an upward force. Again, we call that the normal force on the box by the floor. Now, this box is not accelerating into the floor and it's not launching off the floor. So we know that the net force up and down are equal to 0. So the gravitational force must be equal to the normal force upward. But it says the box is moving at a constant velocity, and the floor exerts a force that resists the box's motion. So the floor, if the box's motion is in that direction, that's the direction the child is pushing the box, the floor must be exerting a force in the opposite direction. So this is a force I could call it an applied force because it says the floor exerts a force. I'm just going to go ahead and call that a friction force because that's what it is, and we will get to that. But this is a friction force on the box by the floor. And since it is constant velocity and we've determined that the acceleration is equal to 0, the net force left and right must also be equal. And so the friction force must be equal to the force applied on the box by the child. One last thing I want to point out here is even though the floor breaks the system circle once, essentially, it exerts two separate forces on this box. It exerts a normal force upward, surface support, and it exerts a resistive force, the friction force, opposite the direction of motion. I hope you all have a great day, and we will continue this discussion next class period.